on canvas once we're done. So in this session, we are going to introduce Monte Carlo simulation. It's based off of two important laws of mathematics. The first one is the law of large numbers, and the second one is the central limit theorem. These two are to some extent related. And then we are going to see how we can use Monte Carlo simulation to solve an integral numerically. Okay, so with that, let's introduce Monte Carlo simulation. First, this is an informal definition of Monte Carlo. It's a model used to predict the probability of a variety of outcomes when the potential for random variables is present. Let me do this. Okay. So again, we are working with probability, random number generation, and this time you're gonna see how they are used for estimating the expected value of a random variable. I hope that everyone could attend the meeting on time. It's a little distracting for me to keep admitting people. Okay, so let's move forward. This is a more official definition of Monte Carlo simulation. It's used to solve a problem numerically in which random variables are involved and whose solution by analytical methods is too complex or impossible. Okay, first of all, let me pause here. Does anyone know what is the difference between numerical and analytical solutions? Either here in classroom or in the Zoom meeting, you can type or unmute yourself. Any ideas? You can explain it in, for example, in an example. Let's say you want to solve a problem. Let's say you have a mathematical function and you want to find its integral, right? So if you have the functional form of that function and you currently know by math how to calculate the integral, then you have an analytical solution, right? For example, if f of x equals x squared, right? We know that the integral is what? The integral of x squared.
X cubed over 3.
Yes, is 1 divided by 3 times x cubed, right? That's what we know from math. And that's an analytical solution for that integral. But if you have a very complex function, which is made of different terms, and we don't know the answer analytically, which is in fact the common case in many applications, then we need to use or employ some numerical methods to estimate the answer. And Monte Carlo simulation is one of those very well-known methods for answering to the complex problems numerically. You get to see what I mean when I say estimation, right? We need to work with probability in order to come up with that. But that's the gist of it. And with that, we have, in addition, the use of simulation allows you to test the effects of changes in the input variables or in the output function more easily and with a high degree of detail. So you get to see that once you have the numerical solution for a problem, then you get to test different scenarios, and that's very helpful. You might be wondering where the name is coming from, Monte Carlo. In fact, in World War II, there were two scientists who were part of the Manhattan Project at the Los Alamos Nuclear Research Center. And then they replaced the parameters of the equation that describe the dynamics of nuclear explosions with a set of random numbers. So it's a very, very sensitive problem and a very complex problem, yet using random numbers was very helpful. And then they decided to name this method as Monte Carlo, which is a very famous casino in Monaco. It somehow represents the uncertainty and probability of the uncertainty or the uncertain nature of the solution. You get to see what I mean when we talk about probability and uncertainty. So this is like a very high-level description of what Monte Carlo does when we want to estimate parameters. As I mentioned earlier, the primary objective of Monte Carlo method is to estimate a parameter representative of a population. And to do so, the calculator generates a series of n random numbers that make up the sample of the population in question. So you have a big population and you are going to just generate a smaller, much smaller set of samples. And based off of what you observe in your samples, you're gonna make some conclusions about the main population. Okay, so that's the brief introduction to Monte Carlo. And here, for example, we suppose that we want to evaluate a parameter A, currently unknown, which can be interpreted as the average value of a random variable. So let's say that you have that parameter A, which is unknown, and by using some pseudo-random number generators, you create some samples with some distributions. You take the average of those samples, and that average should somehow estimate for you the expected value of the unknown parameter. Okay? So we're gradually introducing Monte Carlo simulation step by step. I don't want to overwhelm you with all the theories. It's just informal definitions, and then we get to see some more formal definitions. So again, the Monte Carlo method is essentially a numerical method for calculating the expected value of a random variable. Recall that the expected value of a random variable is basically the average of the values that the random variable can take, right? So we talked about your GPA, and then you want, if your grades are a random variable, which I hope they're not. If they are random variables, then you can just find the values of that random variable for some samples, and then you find the average, which is the expected value of that random variable. Okay, so to obtain the result, the Monte Carlo method is based on two fundamental theorems, the law of large numbers and the central limit theorem. So let's look at these two definitions together. The law of large numbers is pretty trivial. It says that the average of the results obtained from a large number of trials should be close to the expected value and tends to become closer to the expected value as more trials are performed. Okay, so again, recall that we defined the expected value of a random variable last week. If it's a discrete random variable, the expected value is basically the summation of the values multiplied by the function values of the xi is basically the probability. The probability times the functional value at xi, and if it's a continuous random variable, instead of summation, you just simply have the integral. Okay. We had these different definitions before. This is just a reminder. And with that, let's take a look at one simple example together to understand this better. So we all are familiar now with flipping a coin, the probability and everything. It's one of the simplest examples. And we talked to each other when we introduced the chi-square test that when you just have a very limited number of observations, they may not necessarily show you the exact probability that we expect to see from the theory, right? So theoretically speaking, we know that if we flip the coin n number of times, half of it should be tails and half of it should be heads, and the other half should be tails. But we know that, in observation, it does not necessarily follow that 50% exactly, right? This is all we know, but the main question here is that does adding more observations make any changes or not? And here is, an example that you see in this figure, in this table. In their observations, in their experiments, what they did was to flip the coin in three different experiments, right? So in the first one, you have 10 number of flips, 4 of them are heads, so the probability of having a head is 40%. And if you increase the number of observations, you can see that this probability converges to 50% that is expected from theory. This is the law of large numbers, right? So if you have a good number of observations, a big number of samples, then the average of your samples converges to the expected value of that random value. Is that clear to everyone? You also check the chat. Okay. Gonna pause here, make sure that everyone is getting this. It should be pretty trivial. We somehow know that by having more and more sample points or a large number of observations, what we expect to see in practice converges to what we have in theory. And this is basically the law of large numbers. Okay, so with that, let's also have a more formal definition. The law of large numbers allows you to determine the centers and weights of a Monte Carlo analysis for the estimate of the finite integrals, but does not say how large the numbers. Okay, so this one is related to the application that I'm going to show you later, but have this law of large number in mind, because later when we want to see that application together, it will be needed. Okay, so the other thing that we need to know relevant to Monte Carlo simulation is called central limit theory. Okay, so what it says is that if you have a very, very big population and it's hard, it's expensive, or, in practice, for some reasons, it's not possible for you to study the entire population, then given a sample of that population, you can learn about the main population. In fact, what happens is that when you have a sample of the entire population, the mean of the samples is going to have a normal distribution whose mean is the mean of the main population. Okay, that's a very big claim. That's really helpful in statistical analysis. Let me make you an example here. Let's say you have the population of Cal State LA, the student population of Cal State LA, which last time I checked was more than 21,000, right? So for some reasons, you're interested in studying the average height of the students, okay? So one way to run this experiment is to go and measure the height of all the students one by one. It's gonna take some time, so you may want to do that, or you may say that, you know what, I'm going to just sample the entire population and then find the average height of the sample, okay? If you do the sampling correctly, there are some characteristics to the sampling that we're going to learn later. But let's say that you have a fair sampling and the size of your sample is big enough, then the mean of your sample is going to be the expected value of the original population. So there is no need that you go and measure the heights of all the 21,000 students. You can just have a smaller sample, run the experiment, and find the mean. Okay? In addition to that, we also know that the mean of the sample is going to have a normal distribution. If you remember, normal distribution is characterized by its mean, mu, and its standard deviation, sigma, right? Sigma squared. But I'm not going through the details of that. I'm just telling you very briefly that once you have that sampling, it gives you the central limit theorem, gives you very interesting information about the original population. So you can relate the two very well. But what we need for now for understanding Monte Carlo is that the mean of the sample is going to be the mean of the original population when you have a large number of samples. Okay? This is again what we learned from the law of large numbers. In central limit theorem, though, you also learn about the distribution of the means, but as I said, I'm not going through the details of that. Here is a more formal definition of central limit theorem. It basically says that, as I mentioned earlier, if you have a large number of samples, then the mean of the sample is going to be a normal or a Gaussian distribution. And here is also something relevant to Monte Carlo simulation. The central limit theorem can be summarized with the following definition. Given a data set with unknown distribution, we're talking about the original population. The sample's means will approximate or will follow a normal distribution, for which mu, or the mean of the sample, is going to be the mu of the original population. If you're interested in its standard deviation, you can Google it, but that is also something relevant to the original population. So you get to see the main characteristics of this distribution once you do the sampling, and you can relate it to the original population. It's very neat and it's very helpful. But anyhow, I think it's gonna be more clear what we are, really talking about if we get to see it in application, okay? So let's stop the theory and let's look at one example together, which is about numerical integration using Monte Carlo simulation. We do have the Python implementation in the textbook Get repo, and we are going to see that as well, okay? So let's look at the problem together first, and then we are going to see how to solve it with Monte Carlo simulation. Recall that analytical solutions are those that give you exact answers, and they are very accurate. However, in many problems, we do not have analytical solutions for the problems, and we need to approximate them using numerical solutions. And this is one of the cases. Finding the integral can be pretty complex. So in this example, we are going to analyze the problem of a definite integral. You remember what a definite integral is? Anyone? Definite or definite? So it happens when you have upper bound and lower bound in the integral. It's not going from, minus infinity to plus infinity. Yes, thank you, Zain. They are within a range or a bound. Okay, so we are going to find or analyze a problem of a definite integral In the simplest cases, there are methods for integration that foresee the use of techniques such as integration by parts, integration by replacement, and so on. You might have heard these methods in your calculus courses before, if you remember. In more complex situations, though, it is necessary to adopt numerical methods that involve the use of computer. In these cases, the Monte Carlo simulation provides a simple solution that is particularly useful in cases of multidimensional integral. In the example that I'm going to share with you, we have just a one-dimensional integral. So there is just one random variable x and y, which is f of x. Okay, so it's very, very simple, but you can easily, generalize it for multidimensional integrals. And it's for the finite integral. Again, you can somehow think about more complex situations where the upper bound or lower bounds are not defined, and you can somehow approximate it within a certain range. But we are going to look at a very simple case together. Okay. So let's see what we have. So as you can see, we have a function f of x, right? So x is our x is our variable, which in this case is changing from a to b. So this is the range for x. And then y, which is the values that it can get, goes from 0 to u, right? So f of x is this function, and if you want to find the integral by the definition, then you are interested in the area below the curve, right? Which is the gray area. You're following me? Everyone is okay? Okay. So if we have an analytical solution for this problem, then it would exactly calculate for us the gray area. However, let's say we don't have that, or it's very complex, or it's very expensive, so we want to approximate that. So you should be following me here very carefully because we are making some definitions here. After defining x and y, which are moving in these two ranges, then you can see that we have this rectangle. I'm also going to show it in the slide so the people in Zoom can also follow me. You can see this rectangle or this box, right? And you can also see the gray area. Okay, so what we are interested, it's very easy to find the area of this box, right? We know A and B, and by a simple process, we can also, for example, find the maximum value of that function. So we can also find u, and based off of that, we can find the area or the area of this box. But what is not clear is that how many, or the gray area is what we are interested in. And when it comes to Monte Carlo simulation, recall that we are generating some random numbers, right? So if I'm generating some random numbers in this box, two cases may happen, right? Some of those random numbers are less than or equal to f of x, and some are not. They are in the white area, okay? So if I can find how many of them are less than or equal to f of x for each randomly generated value of x, then I can come up with the probability, and with that I can come up with the numerical estimation of that integral. Okay? So this is how we are going to approach this problem. We are going to generate some random numbers, x and y's, which are random numbers, in this box. When x and y's are generated, they show us one point in this two-dimensional space, right? We can compare the value of that point with the corresponding point on the curve. And if the value of that point is less than f of x, then we say that it's in the gray area. We're interested in that. If it's not, it's in the white area. And using that, we can estimate the integral of this function. So let's follow me carefully here where we have these definitions. In Monte Carlo simulation, x and y both represent random numbers, okay? So yes, this is a one-dimensional integral. However, we are creating x and y values both randomly, okay? At this point, we can consider a point on the plane of the Cartesian coordinate x and y. Our goal is to determine the probability that this point is within the area highlighted in the previous diagram. That is, y is less than or equal to f of x. We can identify two areas, as I mentioned before. Let's call the gray area, which we are interested in, or the area subtended by the function f, as I. So I is in fact what we want to calculate. And then the area A of the rectangle with base A to B and height U. And if we want to write what we just said at the beginning mathematically, then this is what we are interested in, the probability of y's that are less than or equal to f of x, right? So in fact, if we remember, the probability is the number of outcomes that you're interested in divided by the size of the sample solution, right? In this case, we are, instead of working with some discrete numbers, though, we have this continuous part of the space. So if I want to define this probability, the part that I'm interested in is I, which is the integral that we want to calculate, the gray area, divided by the sample space, which is A, which is defined here. It's the size of the rectangle, the area of the rectangle. Okay. So if I want to calculate this probability based off of what is defined here, I just simply divide I by A. I is something that I don't know, so we're gonna work on that. By A, which is the rectangle area, is B minus A, which shows us this segment multiplied by U, right? Because it starts from 0 here. So the area of the box, or A, is B minus A multiplied by U. Any questions?
So I'm just a little bit curious now. If we go back to the previous slide real quick.
Previous slide.
Are we gonna figure out how we're gonna account for the non-shaded area in a moment?
Yeah, you're gonna see that.
Okay.
Yeah. You'll see that we are going to generate random numbers, as I mentioned earlier, x and y. And each time that a random number is generated, we compare its value with f of x. So if you generate x1 and y1 in this space, right? For example, here, we have x1 and we have y1. So I can compare f of x1 with y, right? And if y is less than or equal to f of x1, then we are in the gray area.
Okay.
If I generate a random number here, x2 and y2, I know what is x2, right? So I have f of x2, the value of the function in that point. I also have y2, right?
Yeah.
So I compare the two, and this is not in the area that I'm interested in.
Okay.
Okay. Having these two numbers, you can come up with the probability and then later calculate the integral. It's really interesting. And we are going to see how accurate Monte Carlo simulation is. We have the implementation, so I'm going to show that to you. Any other questions? Okay, so let's move forward. Okay, so as I mentioned earlier, we are going to generate random numbers on the X and Y axis, right? So we have Xi in this range of A to B and Yi between 0 to U. And we are generating random numbers. And here we are working on that probability step by step, okay? So what we define here is that so recall that every time we are interested in yi's, which are less than or equal to f of xi, the gray area, and we, I mean, those numbers who have this feature, meaning that they are in the gray area, we count them and we use M, capital M, for showing the number of randomly generated numbers which are in the gray area, okay? So we have M as those numbers which are good, and then N, capital N, is the total number of random numbers that we generated, okay? So it gives us mu, which is, again, the probability of having values which are in the gray area. So you can look at this integral from another perspective. This is, again, related to what I showed you earlier. So this time, what we are saying is that the integral I that I'm interested in, the gray area, is approximated by this probability, m divided by n, or the probability of having a number which is in the gray area, multiplied by, this is showing the area of the whole box, right? So basically what it's trying to tell us, I mean, this is the box, right? The main box that we have, right? But not all the numbers that we are generating is in that box, right? Okay, let me do a better job explaining. We know that the probability is always between 0 to 1, right? So the numbers that we are generating, m divided by n, is always between 0 to 1. This is telling us the area of the entire box. And apparently we are just having a part of it. And a part of it is determined by the probability of the numbers which are below the curve. Okay, so let us look at the code. I guess it tells us everything very well. But that's basically it. So instead of going through all the complexities of, you know, I have a numerical function, how would I find the integral? If it's a sine function, if it's a cosine function, if it's whatever function that is, if you can find, you know, the ranges A to B, and if you can find the maximum value of that function within that area, assuming that there is just one max, there is no mean max, okay? If you could do that, if you simplify the problem, then you just simply generate some random numbers, and then you can numerically approximate that integral, okay? So let's look at this code together, and then I'm going to run it in my Chem Compute account. I also let you know where the code is. We are going to play with some numbers together to see how that affects the final result. So here we are defining a function. This time we have x squared, right? So we all know what x squared is. You know, the root is in 0, and then it goes up exponentially. We are interested in this range, 0 to 3, and we are having 1 million number of steps in this case. Okay, so we are going to generate 1 million random numbers in this case. And then we are also defining 4 variables here, which are related to the gray area and the white area that I showed you earlier, okay? So X and Y integral are containing those X and Y values which are under the curve and we're interested in. X rectangle and Y rectangle are containing the values which are in the white area that we are not interested in, okay? We are setting a seed here for the, okay, we are using random, which I guess now you're all familiar with. This is a built-in, this is the library in Python which generates for us random numbers. You have it for project 1, right? So we are using that for generating random numbers, and we are setting the seed to 2 in order to replicate that result over and over again. And then the function that we have x squared, this is a new definition of function in Python. Are you familiar with that? So usually we have this, right, when we want to define a new function, but this is an inline definition of a function. You don't really define it, just in line, you explain what it is, and then you use it. So we are defining our function as x squared. You need this keyword lambda in order to define an inline function. Okay, it's not very important, but maybe you get to see it in some Python codes. We have 1 million number of steps, and these are the variables that I defined for you. And every time, as I explained earlier, we are going to see whether the value of the randomly generated number is, less than f of x or not. Before that, though, if you have a function, you have no idea where the maximum value is, right? So what you need to do is to somehow, what's that? You just go from, the starting point, which is A here, to the end point, which is B, and then you're gonna take this small step. So if you have 1 million number of steps, you're gonna start from A, and then your D or delta, your small steps are in fact the range, which is B minus I multiplied, no, this is basically just showing you're keeping the two, divided by the number of steps, right? So this is showing the step size. You start from A, you go a little bit to the right, to the right, to the right, and each time you see whether the values are less than y min or greater than y max in order to store the mean and max of your function. So this is mean max detection that we have. Shouldn't be that hard, especially for simple functions. You can visually understand what it's doing. Oh, sorry. And this is in fact your Monte Carlo simulation, okay? So again, we know how to find the area of the box, right? It's B minus E multiplied by Y max minus Y mean. And in the previous step, we found Y max and Y mean. So we have that. That's the area of the box. And determines the number of samples or the number of randomly generated numbers that you're going to have in this experiment. And M is the number of points that are in the gray area under the curve, right? So what you're doing again, this is somehow the definition of integral, right? You start from A and you go each time a small step to the right in this case, right? So you go another small step. You also have your Y, right? So sorry for that. So here we are actually generating new random numbers, right? So you start from A. This is B minus A, right? Recall that the random library in Python generates for you random numbers between 0 and 1, right? So if the number is between 0 and 1, I need to multiply it by the line segment that I'm going to examine for the x-axis, right? So b minus a is the range that I have for x. I multiply it by this random number that I'm generating. Similar thing for the y values, right? I start from y mean, for those who are in the Zoom room, I start from y mean, and then if I want to generate a new number using random, it gives me, or it returns a number between 0 to 1, I multiply it by the range, by the feasible range for the y values, so I know how much I should go up from y mean, okay? So every time that a new random number is generated, I have the function value f of x, right? I can compare the y value which I generated with f of x. If y is less than or equal to f of x, it means that it's under the curve and I'm going to keep it. I also increment m, which is storing for me the number of randomly generated numbers which are under the curve. Otherwise, I only store it in the other array, which is helpful when I want to visualize the outcome. It's not really helping us with calculating the integral. It's mainly for visualization. So finally, your numerical integral is m, the randomly generated numbers which are under the curve, divided by n. N is a fixed number, right? Here we have 1 million sample points, so it's clear from the beginning. Multiplied by a, and again, a is clear. It's the area of the box. So knowing the ranges for a and b, we can calculate a easily. What is not clear and you need to determine is m, which is the number of randomly generated numbers that are under the curve. Okay, and this is the description of what I explained to you. And in this case, I'm going to run the code for you. I also encourage you to take a look at it. We still have some time. And we are going to see that by, for example, 1 million sample points, randomly generated numbers, we can approximate this integral very accurately, right? So we all know that x squared, its integral is 1 divided by 3 times x to the power of 3, right? So if it's the finite integral, you have this, you also have this constant. It's going from 3 to 0. You just replace x with 3, minus you replace x with 0, and that gives you 9. I guess you didn't really need to do that. It's very straightforward, but this is, the entire math behind it. So the analytical solution for this problem is 9. This is what we know. And if we run this numerical solution, it gives us 8.99. It continues, but we can stay here. So it's 8.99. After generating 1 million random numbers, we could approximate the integral this accurately. And we are going to, change the code a little bit together in order to see what if we have fewer number of sample points. Is it going to change the accuracy drastically or not? But this is really neat. We did not really solve the problem. We just generated some random numbers. And then we compared the values of those random numbers with f of x, right? F of x is given to us. We just don't know its integral. And that's pretty much it. It's really neat. It's very simple, yet it's calculating for you something very, very complex. Yes, if your function is somehow more complicated, as I said, if you have multiple means and maxes, then you need to partition it. And for each partition, you calculate the integral. Or, if there are some other complexities, it may require some additional steps. But for this case, you can see that it's very simple. You just need to be comfortable with probabilities, and then the computer does the numerical approximation for you. Okay, so then in the code, we have visual representation. I'm not going through the details of it now. Once you have, those arrays, you just simply plot them with different colors, and we are going to look at it together. Okay, so let me see. Yeah, so what I suggest to you, since we have some time here, let's open your laptop, and what I need to do, what I need you to do is to go to the GitHub repo of the textbook. I'm on my Chem Compute account and I have cloned the code. So I already have everything here. I hope you do, either locally on your computer or on Chem Compute, which is our web-based application for running the code. So I give you some time. If you already have it, you just go to chapter 4 and you see that there are 3 pieces of Python code here. You can take a look at central limit theorem later. We didn't really talk about the code here, but what is implemented here should make sense to you now after, defining the theorem. What I want you to do though is to run numerical integration.py. So if you are on your computer, you can run it. If you are on Chem Compute, it doesn't run like that. So you just need to open this Python function, copy it, and then here in new, you create a new Jupyter notebook. I did this earlier. So you just copy and paste the code here in a code block and then run it. It takes a few seconds for it to generate for you 1 million random numbers. And you should be able to see something like this. So I'm gonna pause here for a few minutes. I wanna make sure that you could run it successfully.
Which chapter was it in again?
4, chapter 4, and it's numerical integration. .py.
Thank you, Professor.
Sure.
Thanks, Carl.
So make sure you can run it successfully. You should get 2 outputs. One is a numerical integration, the number, which should be 8.99. And the second one is the visual presentation of what the code did for you. Okay, those are with us in the Zoom meeting. Let me know if you have any problems with running the code. It should be pretty straightforward. Yes.
We're using like Monte Carlo. We're always going to try to use like a big number of.
Yes.
Is there anything that's too big of sample, like
To determine how big we should go?
like a bit of 1 million, like
Yeah, that's a good question.
is
There is no generic, well, so there are different methods for doing so. Now I'm going to show you, if you play with this number, you get to see the integral, right? The value here. And based off of your resources, you may say that, I don't want to go above this number of CPU hours, for instance, so that limits my calculation. If you are fine with the resources, you should set a cap on the accuracy, right? So you may want to say, okay, this much error is fine with me. So it's going to be a little complex to calculate that, though. We didn't go through that because, for instance, for the case of integral calculation, if you want to set a cap on the accuracy, then, you need to, I should think about it, how to write it mathematically. But what I can say is that for simple problems, we usually start with something and we look at the numbers, and usually accuracy is what is important for us. So we say that, For the simple case, we're far from the analytical references, so we want to make it more and more accurate. And for the cases that we don't have any references, based off of what we did earlier, we just go with the same setting. Okay, this comes from practice, so I don't have like rigorous mathematical theorems to support that. Okay, let's spend 1 more minute here. Any questions about running the code? If it's running successfully on your computers, I want you to spend some time on the code. I already explained to you what it's doing, so it should be pretty straightforward. What I didn't explain very thoroughly was the plot that is created here, okay? So I want you to tell me what exactly the yellow, red, and blue dots are telling us. So you tell me that first, and we are going to then change some numbers in the code to see how these dots are changing accordingly. But can anyone tell me what these dots are? Since we have 1 million number of random numbers here, you get to see it as a solid color, so it's hard to tell whether there are dots or not. But believe me that there are dots, okay? So when we reduce the number of sample points, you get to see that there are discrete dots. So what's going on in here? Can anyone tell me?
Red is the function, and then blue is the one that's the dots that are under the function. I think we set that as M.
Yes.
And then yellow is all the dots not above the function.
Yes, right. So here we have our function is x squared, right? So it goes from 0 to 3, and the red line is showing you the function, the analytical representation of the function. Again, if you are in a high dimension, if the function is complex, there is no way you can see it easily. You just trust what a numerical method is doing for you, right? Here is a simple case. It's a one-dimensional, easy case where we can see the function, okay? So when we see that, it should be very straightforward. When we generate the numbers, they're either under the curve or they are not. And based off of that, we calculated the probability, m divided by n, and we multiplied it by the size of the box, okay? So now what I want you to do is to change n in order to see how it affects the final result. So let's go with a very small number. Let's just generate 1,000 random numbers. Run the code and see what happens. Okay. As I told you, there are discrete dots, right? Now that we have only 1,000 of them, you get to see that we have more sparse sampling of the space. The blue ones are still under the curve, the yellow ones are above the curve. Even with 1,000 sample points, the result is not that bad. I mean, the analytical solution is 9. It's generating for us 9.28. It's not that bad. But if we keep incrementing the number of sample points, then you get to see that, the approximation gets more and more and more accurate. So we are now with how many? 10,000 number of sample points. What we approximated is 8.98. It's, again, a really great approximation. We go to 1 million. $8.99. Now it's, getting closer or converging to 9. And I guess what we had in the original code was 10 million, right? Sorry, 1 million. Is it? This is 1 million. Okay, so previously I had 100K. So you can see the convergence, but as I showed you, even with a small, pretty small number of samples, and the result was not that bad at all. So this is, one application of Monte Carlo simulation. For your next project, we are going to estimate the value of pi using Monte Carlo simulation. That's also a very interesting application of Monte Carlo. We all know what pi is, 3.14 something, right? But that something can be approximated more accurately using Monte Carlo. We are going to see that together. The code is already here in the repo, so you can take a look at it if you are interested. We have simulating pi.py. You can take a look at it. For project 2, though, we are going to run serial and parallel implementation of simulating pi. So we are going to work with MPI and message passing interaction in which is a method for parallel calculation, and we are going to run it on Delta. But for now, this is what we have for today. I'm going to switch back to the slides. Is there any question from the people here or in the Zoom meeting? Is everything clear about the code, about the output? Okay, so if everything is okay, I'm going to go back to the slides. This is also a screenshot of what I showed you earlier. And I also, yes, that's pretty much it. Once you run the code, you also get to see the results, so you can compare different scenarios numerically.